Hello and welcome to this session about time series forecasting. My name is Fabian Temme and I'm a data scientist at RapidMiner. A few words about myself. I did my PhD in astroparticle physics at the University of Dortmund in Germany, and already then I used RapidMiner to analyze the telescope data. And end of 2016 I joined the RapidMiner research team, and I'm working on government-funded research projects, mainly in the data science area, and I'm focusing on time series analysis. Which brings me to the topic of this session, the time series extension. The time series extension is a revamp of the old value series extension, and we're focusing on improved usability, documentation, and added functionality. Since RapidMiner Studio 9.0, the time series extension is bundled with the main product, so you can see here on the right that you can find the time series operators under modeling, time series, and then the different kind of tasks you want to apply. Additional features will be released with every major RapidMiner Studio release, so we will add more and more features with next releases. To showcase time series capabilities of RapidMiner, the best way is to analyze a real data set. So what I will use in this session is a Kaggle data set about weather data. It's hourly weather data from mainly US cities, some from Israel, some from Canada, between the October 2012 until the November of 2017. Different weather attributes are in this dataset: temperature, humidity, pressure, wind speed, wind direction, and the weather description. And you can see here's the link to the dataset itself. I did some small preprocessing, like for example converting the temperature from Kelvin to Fahrenheit. What we will do in this session, we will do different steps of a classical time series analysis. We start with preprocessing, cleaning time series. Then we do a fast Fourier transformation to get some insight into the data. After that, we're doing aggregating of the data. Then we'll come to some more classic time series analysis, the decomposition analysis of the time series. And then we will do forecasting, first with windowing, then with advanced feature generation, and then with ARIMA. So I will start with a demo. Several features which I will show in this session are added in RapidMiner Studio 9.1. And we will start now with the preprocessing. So I will call this 01 preprocessing process. So as I said, I prepared a little bit of data set, so I took the data from Houston, the weather data, and we will start by having a look into the data. So as you can see here, we have the daytime, we have the humidity, pressure, weather description, wind speed, wind direction, and temperature. You can see there are several numerical attributes in it, but also the nominal, like the weather description, which is really a description of the current weather situation, and also the wind direction is also a nominal value, and the wind speed is an integer, which we should have in mind when we extract features from this. Have a look at the statistics view. So we see the date range from beginning of October of 2012 to November 2017. The humidity, which is obviously a percentage number. The pressure, as I said, the weather description. Interesting, maybe we have one-time volcanic ash in Houston in this date range. You have the wind speed reaching up to 15. And we can also have, for example, look into what the most occurring wind direction was, which is the south. And also we have the temperature of Houston. What we can also see, we have different missing values in it. Normally in a machine learning case, we'd replace these missing values by, for example, the average or something else. But in time series, we want to do something else. So I will scroll down to the first missing value in the data set for pressure, which is here. So we see we want to use the neighboring values to replace this, for example, by the previous value or by the average of the two values. So we go back to the design view and we use replace missing values for series. Here we see we have different features, so just minimize the help text. So I just want to ensure finite values for the different settings. I would suggest to have a look at the help text in general, and you can select the attributes you want to apply the replace missing values on. And we want to use for numerical the average, and for nominal we don't can calculate the average, but there we want to use the previous value, as well as for possible date time, which we don't have in our data, as a time series attribute. We want to override the data, and also we want to store them already as cleaned data. So Houston data cleaned, and we'll have a look. So we see the data seems to look the same, of course, just replace missing values. We see there aren't any missing values anymore in it, and when we scroll down to the row 198, we see this is the average of the two values around it. After we have a clean data set, we can do our first analysis, which is we perform a fast Fourier transformation on the data. So I call this process fast Fourier transformation, and we include our clean data set, and as I said, fast Fourier transformation. You see here we can add also select for which attributes you want to calculate the fast Fourier transformation. Just connect everything and run it and have a look into the results. So what we can see here is the amplitude of our frequency spectrum. So the Fourier transformation calculates the frequency spectrum, and we can see here the different entries, so different amplitudes for the different numerical attributes. And we can also have a look at the chart series plot. For example, have a look into the humidity amplitude series, and we can see that we have, of course, that's typical for a fast Fourier transformation, a really high entry at the first index of our frequencies, and we have also some significant entries in higher frequencies. To have a bit better look, I will go back to the design view and insert a building block, which is called generate frequency, which just creates an ID and a new attribute, which is the frequency itself in 1 per day. And I want to, so that we can have a better look at the small numbers, I want to also apply a logarithm on our amplitude spectrum. And as I don't want to apply to the frequency, I select the frequency as a single attribute but invert the selection, and I don't want to override our attributes, so I get now new attributes which are the logarithm of our data. So these are all time series attributes. Most of the time you have for time series attributes this kind of parameters of time series selection, like of select attributes, which allows you to select the time series attributes you want to apply it on. So I have another look now on these post-processed Fourier transformations. So we have the new frequency, and we will directly have a look in the charts view, series plot, and as we can see, we want to have a look at the, for example, the logarithm of the humidity, and we can more easily identify the peaks in the frequency spectrum. And as I calculated the frequency itself, we want to have it as a index dimension, and we can clearly see we have at 1 per day, 2 per day, 3 per day different entries. And for example, also interesting in the pressure frequency, we have also this 1 per day, which is reasonable for weather data, also half a day for day and night cycle, but also a large entry in the frequency spectrum for 8 per days, which means that we have every 3 an oscillation which a period of every 3 hours in the pressure, which is quite interesting for Houston. So for deeper analysis, we should have a look into what this oscillation is about in our pressure data. So this is about analyzing the frequency spectrum of our weather data by using fast Fourier transformation operator. Another often occurring task in time series analysis is aggregating data. For example, if we have highly dense time series data with way too many examples or way too many data to use them properly, so we want to aggregate them. So this process is therefore called series 3 aggregate data. I start again with inserting our clean data set, and then I use the operator process windows from the time series extension. As you can see here, the process window is a subprocess operator, and what it does is it creates windows and process the inner subprocess for on each of these windows. So we can define the window size of it, so 24, so exactly 1 day. And we could also create overlapping windows, as we currently just want to aggregate our data. We don't want to have any overlapping, and also we don't want to create any horizons. But we have an index attribute, which is our datetime attribute. And as we have an index attribute, we also want to create this last index in window attribute, which we, with the effect of the parameter, we'll see later. As you can see here, we can execute this in parallel if our license allows. So as I said, this divides our data into windows, and inside we can now go into it and any time series operators which work then on the window data set. So the window, as you can see here, this is 24 examples. These are 24 examples as our window size. So as I want to aggregate, I will start with extracting some features of each of the window, and we'll start with the extract mode. So extract mode is the extracting the most frequent value of our data, and this I want to use to extract for weather description wind direction. These are 2 nominal values, which is reasonable to have the most frequent value, but also for our wind speed, because the wind speed, as I said, is an integer value, and I don't want to have an average, but I want to have the most frequent wind speed in the window, so in the day. And for the other attributes, I want to have extract aggregates, so insert an extract aggregate, as this is only working on I want to include everything except for the wind speed. As you can see here, the nominal attributes are not listed at all, so it's not working on nominal attributes, of course. So I want to add also, I forgot this in extract mode, I want to add the time series name and ignore infinite values, and I want to do this too. And for the features, I just want to calculate currently the mean of our data. So I just aggregate our whole day window to the mean of the numerical values. So this I could also maybe create with standard RapidMiner operators. But as you can see here, we're in subprocess, we can apply any of our operators on the data. So for example, we can also calculate the differentiate of, for example, our temperature. And then maybe we want to have another extract aggregates of it, and this time we just want to calculate the differentiated temperature. We want to add again the time series name and deselect everything except for the sum, because we maybe want to have the sum of the temperature change in for the whole day. So we have now calculated several features, and we want to merge them together, and therefore I'm using an operator from the operator toolbox extension called merge attributes. Just merge every attribute together. And I prepared a building block which just use set role rename. Oh, that's the wrong building block. I want to renaming the attribute, the others are used outside. So this is renaming by replacing the different feature attributes and changing names. So we want to have a look how this looks like for the window, and we will also start how the window dataset exactly looked out like. And after that we append all our windows together and connect it to the end set. So and reset. So as we see, just go back to the design view. So we are now at the before the extract mode operator. So this is our window dataset. We have the 1st of October from 1 p.m. to the 2nd of October 12 p.m. and we have our dataset, and then we calculated all the different features and merge it together. So we have now the mode, the mean of the different temperature of the different numerical attributes, and for example also of the differentiators, the sum. And then in the next step, so we're going now one window further, we see we have now the 2nd October 1 p.m. to the 3rd October 12 p.m. and so on. So I will remove now all breakpoints to resume the process so that all features are append together. And we see after I renamed all the attributes, so we have now daily data, 2nd October, 3rd October, and so on. We have again our now aggregated data, and we have also, for example, the aggregated temperature change for the days. So this last datetime in window attribute was created because we selected the parameter, I will show you, the parameter add last index in window attribute. So this is always the last index value, so the last datetime window in last datetime value in our window. So it was 12 p.m. of the first window, 12 p.m. of the second window, and when we have an initial attribute and this parameter is selected, the operator automatically puts this attribute to every example set which is connected at a result port. So this creation of the last index attribute is automatically performed by the process window operator. So we can see here how it was created. So when I go back now to the design view, I just want to insert another building block, which is post-processing aggregated. I want to store that, and I want to make a more general algorithm, process out of it. I will create a macro where I store the window size. Start with 24. And I'm using this macro in the parameter. Window size. And I'm also using this in the store operator, so I can now directly create aggregated data sets. So I start with 24-hour dataset we already saw, so we can see here 24-hour dataset, but we can also aggregate to, for example, to windows with a window size of only 6 hours. Of course, takes a little bit longer, since it's also execute parallel, but we have smaller windows. This takes, of course, a bit longer. So now we have the 6-hour dataset, and we could see here in our dataset that we have 6 p.m., 12 a.m., 6 a.m., 12 p.m., and so on. So we have 6-hour windows. So you can imagine, as you can put any operators inside the process windows, you can create really advanced aggregating functions or functions applying on the windows, which make this operator relatively powerful. This is aggregating data with time series. A more of classical kind of time series analysis is decomposition analysis, and hence I'm calling this process decomposition analysis. Decomposition means that the time series is separated into three different components: the trend component, the seasonal component, and the remainder component. Since 9.1 we have two different operators for decomposition, the classic decomposition and the more advanced STL decomposition. I will use this, and I will use the 24-hour data to connect this, and we can see here we can calculate this, for example, only for humidity, pressure, and temperature. And we have an indice attribute, which is our datetime, which we use. And as I selected the 24-hour data, we can specify the seasonality of the data, which is then 365 days, so exactly 1 year. We can see here we have different settings which we can use to configure the STL decomposition. Most of it I want to use the default settings, but for the trend smoothing I select I want to change the trend width, and this allows the trend to vary a little bit more. So you can configure, if you're familiar with the STL decomposition, you configure the decomposition even further, but you can also use default values. So I connect this to the result pause, and I will have a look at the results of this decomposition. So I will directly go to the series chart, and what we can see is when we have the humidity, for example, we can see we have a trend component extracted, and we have seasonal and remainder component extracted. And maybe this is directly, you can see it's easy, you can see it in the temperature. You can see we have our original data, which is in red, and we see a trend was extracted, which is basically a linear line, but with some small variations over the years. We see there's a clear seasonal component, which is reasonable. We have winter and summer temperatures, and we see that we have a remainder component, which is just the remainder between the trend and the seasonal from the original time series, and we see that, for example, also larger entries in the winter months. And when we have a look at the pressure, for example, we can see we have a clear trend, of course, in the winter 2014 to 2015. On the spring we have higher pressure values, and what we can also see there is a clear seasonal component in our data. So which is maybe only hinted in our original data, we can clearly extract from our data set. So decomposition allows us to get a really insight in our data, get insight into trends of our data and seasonal components which are maybe not obvious in the first look, and which allows us to be used in further analysis, for example, by keeping this in mind when we're forecasting, for example, by choosing window sizes or other operators. So this is how to apply decomposition on time series data with RapidMiner. One of the main goals of time series analysis is forecasting future values. We will start with forecasting by using the windowing operator, and hence I'm calling the process exactly this, forecasting with windowing. So I'm using the 24-hour weather data, and I'm using the windowing operator from the time series extension. So the parameter set of the windowing operator looks similar to the one of the process windows. We create again windows. So we have an init attribute, and we specify a window size to 7. So we want to use the data of the last 7 days, also of the last week, to forecast the weather of the next day. We will use now overlapping windows with a step size of 1, which means the windows are just moved every step one step further. In this case, we want to create a horizon, which is our temperature. So we want to, this will be our label, which our forecasted value. So we want to create one value with an offset of 0, so exactly the day, the temperature on the next day. So let us have a look how this, what the operator does. So the operator just creates attributes which contains the, for example, the time series data 6 days in the past, 5 days in the past, 4 days in the past, for all attributes selected. So we can see here these are the weather descriptions from 6 days to the actual date, and then the wind speed 6 days in the past to the actual date, and so on. We can clearly see this diagonal structure in our data, which is due to that we have a step size of 1, so it just moved one step further. So of course this moved also one step then to the left. This we have for all our data, as you can see here, for numerical as well as nominal data. And what the operator also creates, because we select this, we create horizon attribute parameter, that the temperature for the next day for the horizon is created and already set to label. Also, an attribute last daytime in window is created, which is an ID attribute, which is just the last index value of the window. So this was the window until the 8th of October. The next window goes until the 9th of October. So this dataset has a structure we already know from machine learning attributes, machine learning tasks. We have regular attributes, and we have a label we want to forecast, to predict. So we can train a standard machine learning model on it. So I go back to the design view and insert another building block, which I prepared, which is forecasting GBT. So what we do inside, we use the window dataset, and inside we do a cross-validation and train a gradient boosted tree. So any machine learning model are just using the gradient boosted tree because it's relatively stable. And then we want to apply the model, and we want to calculate the absolute error and the relative error of our regression for our forecast, because we remember we want to forecast the temperature. So then I have just a name of our model, and I store this model, the test set itself, and the performance in the results. So I retrieve the data, convert it to an example set, which is usable for machine learning, and then train the GBT and store the results. So I will run this now. So I'm training the GBT, of course. This takes a little bit of time to execute. And now just the model. So I go back to the design view, and we see in the result we have temperature forecast. And what is interesting is first the performance. So we have an absolute error of 4 degrees Fahrenheit, and we have a relative error of 6.8%, which is quite well for first approach of forecasting. So when we want to have a look at the test window, we see we have now here a prediction of the future value and the label itself, so we can have a look how good it's fitting. So I select the temperature itself and the prediction. So the prediction is now in blue. So we first see we can follow the summer-winter structure and also the daily fluctuations, and we see that this model has also a little bit under prediction for the summer values, obviously. So this is a simple approach to convert any time series data to a machine learning model, machine learning data set, which a machine learning model can then train on. So this windowing can be applied to any time series data set, and then all the capabilities of RapidMiner in training machine learning models with optimization, the windowing, the window size would be included in the optimization, and so on, can be applied on this time series forecasting problem. Another possibility to perform a forecasting of future values is to use forecasting with advanced feature generation. Hence, this is the name of this process, forecasting with advanced features. I'm using again the 24-hour dataset, and now I'm inserting the process windows operator, which is similar but more advanced than the windowing operator itself. So it has a similar parameter set as a windowing operator. It has again an index attribute, and I'm using 7 days, so 1 week, as the window size. I'm using overlapping windows, so the windows are just move one step further, and I want to create a horizon, which will be our label attribute. And I want to add the last index in window attribute, which means that the last value of the index attribute of each window is added at the end to every example set which is connected to the result output port of our process windows operator inside. You see this later. Also, the horizon attribute is added to each example that there is a connect here. So inside the process windows, I'm inside the process windows operator, I can now add any RapidMiner operator, which is then applied on our window dataset. So I first want to use the differentiate again to perform a differentiation of, for example, our humidity and the pressure. So maybe the differentiation of these two attributes will have additional information helpful to forecast the future temperature values. I don't want to override them because I just want to add them, and then I want to extract aggregates of these, so features, different aggregates of all different numerical attributes. So as I said, extract aggregates is only applicable on numerical attributes, and when I select all, it's of course only applied on numerical attributes. I want to add the time series name. I just don't want to calculate the sum and the geometric mean. Sum and mean is just roughly the same, but all the different other features for the window, the first quartile, median, third quartile, min, max, standard deviation, kurtosis, skewness, I calculate for all numerical values. As I have some differentiated values where the first value is missing, I want to ignore infinite values in this calculation. For the nominal values, I want to extract also now the mode, the most frequent value. So I select the wind direction and the weather description, and I select again add time series name and ignore infinite values. So now I'm using merge attributes from the operator toolbox extension to merge the different feature sets together. You can imagine you can also add any other feature you can think of by using additional operators here. So now I connect it to the outside, and as I said, as the process windows operator has the parameters create horizons selected and add last index in window attribute, this ID and the horizon, so the label attribute, is added to the result output port. So I append now the results of all windows together, and we'll have a look at the result of this process windows. So now, just deselecting these result sets. Now we see we have our ID attribute, the last index, and our horizon, and we see we have different features for wind speed, for humidity, for the pressure, and so on. So we have again a data set which is capable of for machine learning. We have attributes, different features for each windows, and we have a horizon. So we train a machine learning model on it. I insert again this building block, and in the macro which defines the model name, I just call it extract features. And so I've calculated now a feature data set and trained then a gradient boosted tree on it. And as we can see here, we have an absolute error of roughly 5 degrees Fahrenheit and a relative error of 8%, which is a little bit larger than the one which we achieved with standard windowing. But we can also see and look how well it fits our temperature series. So this is the original one, and this is the one which is predicted. And again, we get the variations roughly, but we underestimate the temperature in the summer. So when we set up a process with even more advanced feature generation, we can use these process windows to generate any feature of a window and use this to train then any machine learning model with RapidMiner. So we combine both feature generation and machine learning with RapidMiner and have a powerful time series analysis forecasting capabilities. A more classic approach of forecasting is using statistical models. In this example, I will using an ARIMA model to forecast future temperature values. So this process is called forecasting with ARIMA. I'm using the 24-hour weather dataset of Houston, and I'm using the operator forecast validation. This is similar to the cross-validation operator, but can be used to validate a forecast model like the ARIMA model. As the ARIMA model is only univariate, I just select the time series equal to temperature, and I set it as an indice attribute. And the forecast validation operator divides the dataset into a training window. I'm using a window size of 100, so 100 days, and into a test window, and I want to test it on 7 days in the future. So in contrast to machine learning models trained on, for example, a window dataset, an ARIMA model can forecast several days in the future, while a machine learning model can normally only forecast one specific value for one horizon offset. So inside the forecast validation, which is also executed parallel, as you can see here, I insert now the ARIMA model, which is trained on the training data set for the temperature, and it also has the daytime, and I'm using here PDQ201. I tested this a bit before. For a better explanation, I would recommend to read help text and further informations. I connect the forecast model to the model output port, and in the performance, in the testing phase, I want to calculate the performance on our testing window. And as the horizon of the forecast validation operator was set to 7, we will test the performance on 7 days. But we will insert breakpoints before the ARIMA and the performance operator to have a look how the different training window and testing windows looks like. So I just connect this together, and I just wanted to have also the data as a test output set, so I can have a look in the test set and the performance. So this is the training window. We see we have 100 examples starting with the 2nd of October, 12 p.m., and we just have our time series data. So now the model is trained on, and what we can see here is we have our January the 1st until January the 16th. This is our test window with the original real temperature value and the forecast of the ARIMA. and also a forecast position and the last date time of the training window, which you can see is the day before the 10th of January, the 9th of January. And when we now go one step further, the training window is just moved one day. So we have 3rd of October, 100 examples, and the test window starts from 11th of January, and the last date time is the 10th January. And again, real values and forecasted values. On this, the performance will be calculated. To resume the process, I remove all breakpoints and just let the process run through. And now we get an ARIMA model which we could apply on to perform a forecast of future values. As this performance is calculated on all different on all 7 days, I want to compare the performance only for the prediction of the next day. So therefore I prepared a building block which does a small trick. So I'm only using the forecast position 1, so the next value forecasted, and do a dummy validation without applying the model, just calculating the performance on this. So this is exactly the same cross-validation performance values which can be compared to the one of the machine learning models for windowing and advanced feature generation, which were in the processes 5 and 6. And I store also these as results. So I run this process again. So we see the absolute error for predicting the next day is only 4 degrees Fahrenheit, or 3.8, 3.9, and it's only 6%. And when we have a look at the test data, we see that we have the temperature, the original temperature, and the forecast, which fits quite well. So this would be how to create a statistical ARIMA model to forecast the temperature data or any other time series with RapidMiner. This was time series analysis and forecasting with RapidMiner. Thank you for your attention. I hope it was informative and helpful. If you have any further questions, feel also free to post them on our community, and have a good day.